Hi, I'm RL from MathinSG.com. So in this video here, I'll be going through the 2024 H2 A-Level Math paper, Paper 1, Question 12. This question is a vector question. So the full work solution can be found here, link in description below. So now let's take a look at the question. We are given air traffic controllers need to locate the exact location of aircraft. They use coordinates X, Y, Z with units in kilometers to locate individual aircraft relative to the base of the control tower, which is at position 000. So we know that the base of the control tower, maybe the control tower look like this. This is the base, and this is where the origin is. All right. Okay, then the horizontal ground is modeled in XY coordinates. Okay, so in other words, the Z coordinates is the vertical one, the height is in terms of Z. All right, now an aircraft flies along the path with equation R equals to this. So this is the equation of the line. The air traffic controllers are situated in the control tower 0.1 kilometer above the base of the control tower. So in other words, right, the air traffic controllers, where are they? They are at 0, 0, 1, right? Because they are 0.1. Okay, because they are situated in the control tower 0.1 kilometer above the base. So the base is at 0, 0, 0. So 0.1 meters above it is 0.1, because we know from this passage here that the Z coordinates is the vertical axis. All right. So now that we have read the first paragraph, which gives us a lot of information about what we need to look at, like for example the coordinates, the XY plane and so on. Next, let's take a look at what we need to do for part A. Due to the atmospheric conditions at the time, the air traffic controllers can only see aircraft that come within 4 kilometers of their position. So in other words, right, this is, so let's assume that this point here is 0, 0, 0.1. So this is where the air traffic controllers are, right? And they can only sense anything that is within 4 kilometers from this position. So the distance between another point and this point must be within 4 kilometers in order for the air controllers to be able to sense them. Next, find the coordinates of this aircraft when it is at its closest point to the air traffic controller. So let's take a look at this. The air traffic controller is a point, right? And the point is 0.1. Okay, this is the air traffic controller. Let me call it the ATC. The ATC is represented by a point. Okay, the aircraft is moving and it follows a flight path, which is given by an equation of a line, right? So the equation of the line is this. So essentially, what are they asking you? So in vectors question, let's ignore all the problem sum questions. What are they actually asking us? Well, in this question, they are trying to ask us what is the shortest distance between the point 0.1 and the line, which is represented by this equation here. Okay? Sorry, so what is the foot of perpendicular from this point 0.1 to the line L? Because at the foot of the perpendicular, this point is closest to the line. This point is closest to the line. All right. So this is what they are asking for. All right. So with that, what can we do? So we just need to go about finding the foot of perpendicular from the point to the line, right? So we will let the foot of perpendicular okay, from, wait, maybe before that, let me first define, let the position of the air traffic controller be A. Okay, then F is the foot of perpendicular from A to L1, and I'm going to define L1 as this so that later I don't need to write it out. Alright, so now I'm going to find OF. So what is OF? Because OF lies on the line, it will take the equation of the line for a particular lambda value. Okay, and then lambda must be real, right? Okay, so next let me find what is AF. So AF is OF minus OA, and I know that A is 0.1. Okay, and I know that AF is perpendicular to the line. So when they are perpendicular, the dot product will be equals to 0. The dot product of AF dot the position vector of the line will be equals to 0. Okay, so do the dot product. Okay, then solving for lambda, you'll get lambda equals to -7/15. Okay, then next I'm going to sub in lambda into this OF to find out what is OF. So OF equals to 4 minus 7/15, 3 plus 7/15, 1 plus 2 minus 7/15. Okay, so this one is 3 8/15, 3 7/15, and 1/15. So in other words, right, the coordinates of the required coordinates. So because this is vector, right, so you need to write required coordinates. So let me write here the answer. Required coordinates okay, so that is the answer for part 1. Part 2, determine whether the air traffic controllers will see this aircraft. So how do you know whether you will see the aircraft or not? Well, you need to look at this one here, right? There's an information. The air traffic controllers can only see the aircraft that come within 4 kilometers of their position. So in other words, right, if AF, we need to check whether AF is lesser than or equals to 4 kilometers or not. So if it's lesser than or equals to 4 kilometers, then it will be able to see. If not, it won't. Okay? So let's do it. So let's find AF. So AF is this equation, right? 4 plus lambda. So AF is equals to 4 plus lambda, and we know that lambda is -7/15. Okay, use your calculator, evaluate the these three values here. You'll get 3 and 8/15. 3 and 7 over 15, negative 1 over 30. Okay, so next let's find mod AF. Mod AF is basically 3 and 8 over 15 square plus 3 and 7 over 15 square plus negative 1 over 30 square. And then we need to square root this whole thing. Okay, typing everything into the calculator will give us around 4.95 kilometers. Okay, which is greater than 4 kilometers. So if the closest distance between A and F is already more than 4, there is no way the air traffic controller will be able to see this aircraft, because the shortest distance between the air traffic controller and the aircraft is already 4.95 kilometers. And the ATC, or the air traffic controllers, can only see the aircraft when their distance is lesser or is within 4 kilometers. Okay, so therefore we can conclude that no, the air traffic controller will not be able to see this aircraft. Next, a drone flies along a path with this equation where k is a positive constant. Determine the possible values of k if the path of the aircraft and the drone do not intersect. Okay, so we know that L1 from the first part, okay, represents the path of the aircraft. So I'm going to copy it here because we will need it. So this one is the aircraft's path. Okay, let me just write it here. Okay, wait, I can't remember. Okay, 431 1 minus 1. Okay, next, this is the path of the drone, right? Let me define it as L2. And I want to write it in the vector equation form because it is easier for us to do the calculation when it's written in this form, which is the Cartesian equation. It's harder for us to do anything with it. So let's write this in the vector equation form. So remember, if you have a form, your A, so x minus A over D equals to y minus B over E, Z minus C over D. Then what do I have? Then the vector equation will be A, B, C plus mu D, E, F, right? So if it's written in this form where x has a coefficient of 1, y has a coefficient of 1, and z has a coefficient of 1. So I'll just rewrite it. I know that I can rewrite this. I can just bring my 2 downwards, right? So this one will be equals to x minus 3 over 2 over 3 over 2, right? Equals to y minus negative 1 over 1 equals to z minus k over minus 1. So rewrite the equation of the drone, the Cartesian equation here, into vector equation. We will have minus 3 minus 1 k plus mu 3 over 2 1 minus 1, and mu is real. Okay, so now that we have the equation of the drone, okay, and the aircraft, they say that they do not intersect, right? So if they do not intersect, that means when we are solving for these values here, right, we do not have consistent values of lambda, k, and mu to satisfy all 3 equations. Okay, so what I'll do is I'll find if they intersect, what are the possible values. Then if they don't intersect, then I will just exclude these values. If aircraft and drone intersect, then I'll form these equations, right? Okay, so to make life easier, the GC should be the one doing the work, right? So I make it in the form that the GC can use easily. Okay, so now that I have done this, okay, I can actually solve. I will find out. So let me use 1 and 2, and let me call this 3 later. So by GC, so if I solve k 1 and 2, then it will give me lambda equals to 7/5, and then my mu gives me 13/3. 13/5. Okay, so if the aircraft and the drone intersect, then k would be the value that is satisfied, or k would be the solution when you start in lambda equals to 7/5 and mu equals to 13/5. But we are told that they do not intersect. If aircraft and drone do not intersect, okay, then I know that 2 7/5 plus 13/5 minus k is not equals to 1, right? Then therefore k cannot be equals to 13/5, but k can be any other values. Okay, so the possible values of k is any real value except for 32/5. All right. Okay. So now that we have done B, let's move on to C. Find the acute angles between the paths of the aircraft and the drone. Okay, so basically they are asking you to find the angle between two lines, right? To find angle between two lines, you basically use cosine and then just follow the formula, right? So required angle, okay, it will be cosine inverse dot product of the direction vector over the modulus of the direction vector, and I need to mod it just in case it is negative because they want acute angle. So this, you should cosine inverse a positive value. Okay, so basically the direction vector of the aircraft is 1 minus 1 2. The direction vector of the drone is 3/2 1 and minus 1. So let's put it in. Okay, for here they say k is equals to 2, okay, for the question, so we'll put in k equals to 2. Okay, then type everything into your calculator, including the cosine inverse. Okay, you will get the answer of 72.7 degrees when rounded off to 1 dp. Oh, wait, oh, don't need, because here is 3/2 1. Oh, don't need, sorry, just ignore me. These are all known values, so we do not need any k value. So basically just use the direction vectors from here that we have, okay, dot product of them over the modulus of this and this. Okay, moving on to part D. It is now given that k equals to 2. The aircraft and the drone are observed on radar to be closest to each other when they are at the point this and this on their respective path. Find the distance between the aircraft and the drone at this instance. So basically it's just asking you distance between these 2 points, right? So required distance 4.2 minus 4 square plus 0.8 minus 3 square plus 0.2 minus 1 square, whole thing square root. Type it into the calculator. They didn't say they want exact values, so can just use the calculator. I get 2.35 kilometers. It's exact. Okay, so that's the answer. Next, by considering the vector between the aircraft and the drone at this instant, determine whether the distance found in part D, part 1 is the shortest distance between the two paths. So now, we know that we have this, the aircraft's path and the drone, right? Okay. And what are we told? They are closest to each other when they are at this point and this point, right? Okay. So 431 and 4.2, 0.8 and 0.2 respectively. So 431. So this is when they are the closest, right? Closest. Actually, I didn't draw it very well. This is not the closest. So maybe let me just draw it this way. Maybe it's in another way. Again, then they say that this is the closest. Okay. So they ask whether it is the shortest distance between the two paths. Okay. So in order for this to be the shortest distance between the two paths, okay, what do we need to show? Well, we need to show that, so let's just assume that I call this point X and I call this point Y. So I have X and this one is Y. This is the drone. Okay. If it is perpendicular, that means X is at the is the closest distance to this line here. Similarly, if Y is perpendicular to the path of the aircraft, right, that is the shortest distance to the aircraft. Okay, so they just want us to find out, is it the shortest distance between the two paths? So what we need to do is we first find what is xy. Okay, so xy is basically ox minus oy. Or maybe let me first define, let ox be this, oy be this. Okay, then let me find what is yx. Okay, which is basically ox minus oy. Okay, so you just do a subtraction. You should get 0.22.2, negative 0.2, 2.2, and then 0.8. Right. Yep. Okay, so next what you need to do is you need to find yx dot the direction vector of the aircraft, which is 1 minus 1, 2, and you realize that it's not equals to 0. You also do yx dot the direction vector of the drone, which is 1.5, 1 minus 1, and you also realize that it is not 0. So we can conclude that the distance found in part D is not the shortest distance between the two paths. Okay? Because they are not perpendicular to each other.